Let's take a look at an example involving exponential growth. Here we have a population of bacteria that is growing, and we're given a couple of data points. We start at time 0 with 2,000 bacteria. 4 hours later, we are dealing with a population of 2,400. And so what we want to do is build an exponential function that models this growth so that we can then predict how many bacteria will be present at midnight. The formula for exponential growth that we typically use when dealing with a population is that the population at time t will be the initial population, which is usually represented p sub 0. You could write it as p of 0, totally fine. And then e raised to the kt, where t is time, and in this case time will be hours, and k is our growth constant for this particular population of bacteria. Based on these two data points, we can get a growth rate or growth constant. So let's go ahead and use the fact that 4 hours after we start, our population goes from 2,000 to 2,400. So P of 4, after 4 hours, we have 2,400. We started with 2,000, so then e to the k we don't know, but t is going to be 4. So I'll write it as 4k as the exponent. Now we can solve this for k. That is going to be the growth constant for this particular population. So to isolate the k term, or the k factor, we'll divide by 2,000. We can simplify this. Certainly the 2 zeros go away, and then we can divide by 4, so we'll get 6/5 on the left. And on the right, we have e to the 4k. Let's go ahead and change our order. Let's put the k term on the left and the constant on the right. Now, k is in the exponent, so this is a little exponential equation. We take the natural log of both sides. The natural log of the left side will have the effect of leaving us with just the exponent, and then we'll have natural log of 6/5 on the right. Almost there. This tells us then that k is equal to 1/4. We divide both sides by 4. Natural log of 6/5. Now if we wanted to type that into our calculator, we could, and we could get an approximation for that. Usually we don't want to approximate this early, but if we did and rounded it to 4 decimal places, we'd have 0.0456. Now let's go back to our equation. So this tells us that our population equation, P of t, is equal to, for this population that starts at 2,000 bacteria, we have this model, if you will. So we replace the k with what it's equal to, and that's all multiplied by t. So that equation right there is called the model for this particular population, and it can predict the population, assuming that it continues to grow exponentially, at any future time. So they say, hey, what is the population at midnight? Well, midnight is 16 hours after 8 a.m. So what we would like to do is figure out the population at time value 16. So P of 16 will be equal to 2,000 e to the, let's see, if we put a 16 in there, 16 multiplied by 1/4 is going to be 4. So this will be our value of the population after 16 hours. And if we type this into our calculator very carefully, remember that the inside of this log will have to be wrapped in parentheses, and remember that this whole exponent will have to be wrapped in parentheses so that you don't get some sort of crazy error. And if you type that into your calculator and we round to the nearest bacteria, you should end up with 4,147 bacteria. Boom.